Welcome. We're going to talk about the Perceptron algorithm. Before we get to the Perceptron algorithm, though, we're going to talk about the basic setting that we're going to look at, which is binary classification. So in a binary classification task, and in fact in many classification tasks, what are we given? We're given a sequence of points. So this is going to be our input data or our training data. And each of these will have two parts to it. Each of them will have a feature vector. And these are each going to be, say, d-dimensional, just to pick some dimension. They're going to be an r to the d. And we're also going to have labels. So these labels, since this is binary classification, we're going to have that yi is in plus minus 1. Now, you might also see binary classification being 0 and 1 rather than plus minus 1, but 0, 1, the plus minus 1 can be more mathematically convenient sometimes for reasons you might see as we proceed. So this is a setting. We have input data, say training data, which is given to us like this. And our goal is to learn or to figure out some function h such that h on the feature vector will give us the output, the label y. So good, this is a little bit abstract, so let's make a concrete example. Let's suppose that, let's talk about grading in a class, or whether people pass a class, not this class, but just in general. So what we're going to do is we're going to imagine our feature vectors are two-dimensional, and they're going to consist of two things. These are going to be your homework score and your exam score in the course. And what the label will be is going to be whether the person passed the class or not. So now here, let's just see some example points. So for example, let's say x1 is equal to, say, 90 on the homeworks, 80 on the final exam, and y1 is that they passed. Naturally, you'd expect if somebody did this well, they're probably going to pass the class. So what would that look like? I just want to draw this. This isn't going to be too helpful now, but we'll see in a little bit later. So this is see how visualizing it will be helpful. So this is going to be something like, okay, this is rough, but let's say this is 80, this is 90, and so we'll represent this as a +1 here. Okay, on the other hand, we have someone else who gets, let's say x2 is equal to, let's say they got a 40 on the homeworks and 30 on the final exam. Well, this is not great, so they are probably going to pass or fail the class. So that on this picture looks something like, maybe like this. And let's say someone else, how do they do? x3, let's say, is equal to, say, 50, and this is going to be equal to 40. And this could go either way depending on how the weighting in the class goes, but let's just say that here, that this is going to be a fail as well. So something like this. So now these are just some example points, but the question is, can we predict what if we're given a further set of homework and exam pairs? So suppose somebody came in with, say, like x equals 50, 60. What is y? Did they pass or not? Can we learn it from this data that we have here? Well, so one thing you could always try to do is, well, we have some training data set. What we can do is just simply memorize exactly what we have in the training data set. This is great in many cases because, you know, if somebody else comes along with a 90 on the homeworks and an 80 on the exam, well, you can point to someone and say, hey, they got a 90 and an 80 and they passed the class. So if you got the same scores, you'd probably pass as well. So, and similarly, if somebody came along with a 40 and a 30, then you'd say they're not going to pass. So this is called a memorization-based approach. However, the tricky part is the fact that we can't really memorize because, as you see right here, we have something that we don't really know. We don't have any answer for this yet because it's not in the training set. So in other words, what we're going to want is not something that just memorizes the function on the input training data. We're really going to want something which can what's known as generalize. Generalize in the sense that if it does well on training data on what we've already seen, we want it to be able to do well on new data that comes out. That's what's known as generalization. And so while we're looking for something like this, we want some h of x is equal to, we want some function which can predict the label based on the feature vector. In particular, we're going to want something which performs well on new data we haven't even seen yet. Now, this might seem impossible, but with the right phrasing, it's actually doable in many kind of broad settings. And it's kind of necessary, right? Because like we saw, we're not always going to have new data that comes at us, which is exactly like the training data that we've already seen. For example, just to use another more exciting example than passing and failing classes, which might be a bit too close to home for some of you. Another thing is, for example, if I show you a cat and then I show you another cat, from those pictures, you might be able to figure out what a cat looks like. Now, if another new cat comes along, you're going to be able to want to identify that as a cat as well. You're going to be able to want to generalize, not just be able to identify the same old cats that you've seen before. So really, this is kind of the goal of learning, to be able to come up with some classifier which will work on the training data you've seen, but also new data. So this gives us this statistical learning type setup. And this is generally what you should always think about in pretty much any machine learning task as what's going on in terms of what type of problem we picture, what type of model we assume. Now, there's a lot of different things which are underspecified here, but this is kind of how you should picture any sort of learning problem. The setting is kind of as follows. Again, we have x1, y1, and so on, all the way up to xn, yn. So this is our training data, which is drawn IID from some unknown distribution P. Now, so that means there's some distribution which, when you draw points from it, it'll give you both feature vectors and labels for those feature vectors according to some function. And they're IID in the sense that the points are drawn identically and independently distributed. So they all come from the same distribution and none of them are correlated with each other. So the goal, so this is our training data, and what we're trying to do is make sure if we're given a new point from the same distribution that it's going to have low error. So in general, our goal is the following: the probability. Sorry, let me clarify. So the goal is to learn some function h. H is going to be a function which takes points in R to the D and maps them to plus minus 1. That is, it'll basically take in a feature vector x and it'll map it to a label plus or minus 1. And what we want to do is we want to learn some function h which has the following type of guarantee. We want that the probability that h on x, probability that this is, say, equal to y, is large, where the probability that we're talking about is where a fresh point x comma y is drawn according to the distribution P. So you can see what this is. We're given a bunch of data from some distribution, and we want to be able to learn some function such that if we drew another point from the same distribution, then it's very likely to be right. Yeah. So that's the goal. And the important thing is generally we don't know what this distribution P is. If we knew this distribution P beforehand, actually we could do something which is known as the Bayes classifier, which is nice and it's very accurate. It's kind of the best you can do. But however, this is a very unrealistic assumption to assume you know where your data is coming from, your distribution of your points. yeah, that's kind of unrealistic. So instead, that machine learning handles the case where they come from some distribution, but we don't necessarily know what that distribution is. There's a few things to comment about this. First of all, we make the assumption that the points are IID. Well, you might think that this is unrealistic. Why would you have independent and identically distributed points? For example, just as a simple, what is a simple way to show you that this is kind of silly? For example, if you had, no, that's not the best example. Let me just say that there could be correlations between your data points. For example, if you take multiple pictures of a cat, and you try to classify all of those, obviously there's going to be some sort of correlation because certain different pictures of the same cat are going to look like each other. So yeah, IID isn't always the most reasonable assumption about any data set, but it's a good starting point, and it's something we can understand things about. So it's often the type of assumption we'll make, though there's some pitfalls which come associated with it. But one thing I'll comment on also is, why do we assume that we have points all coming from the same distribution? And why don't we just say that the worst case, that h of x will not be equal, the probability that, why don't we just look the worst case over all possible feature vectors x? Well, the reason why we actually have to assume some sort of distributional assumption, why we assume all the training data comes from some distribution and then the test point comes from the same distribution, is because otherwise you could have the rug pulled on you, to use casual terms, in the sense that, okay, let me just sort of draw a caricature. Imagine I tell you during training time, I give you a bunch of points such that these points are all good, and then say these points are all bad, or plus or minus, let's just say these are all negative. And then, so that's your training data, it looks something like that. And then at test time, I give you a point that's way over here. Now, what is that? Is that going to be plus or minus? You don't know, because none of the training data really looks like it. And that's one case why you need it to be from the same distribution. Another case you might need it to be from the same distribution is, suppose it's here. Well, what are you going to think? It's going to be like it's going to be like a plus, of course, right? But maybe that's wrong. And in fact, because it's a different distribution, maybe it's a distribution which assigns the opposite labels, and it actually is a minus here. So yeah, generally we use the assumption that we have a bunch of points which kind of look like each other in the training data set, and that a test point, whatever a new data point we're given, is going to be kind of somehow similar to the training data points. So that's the general setting for statistical learning. Now, that's kind of the broad setting. Let me just mention, before we move on to Perceptron, a related setting, which is sometimes useful to think of, particularly when using Perceptron, which you don't know yet, but we're going to talk about in a sec. And it's a setting known as online learning. And in online learning, instead of being given the whole training data ahead of time, we're going to be imagined that we're given the points one by one. And we're going to do a sequence of classifiers. And the idea is we want to basically try to predict each point as we go. And if we get it right, that's great. If not, then we learn something. So this is a bit vague. But let's say we have time steps. So at each time step, at each time, say I equals 1, 2, and so on, kind of on to infinity, we're going to have the following. We're going to receive some xi, so that we're going to get some feature vector. Then what we do is we have to choose some hi, some function, and what we do is we predict that yi hat, our prediction of the label, is going to be equal to the function, the sort of predictor that we chose, applied to this feature vector we received. So we kind of make a prediction of what the answer is. And what we do is we then receive let's just say we observe what yi actually is, and we suffer a mistake if yi does not equal y hat I. And then what we do is we just we update. Yeah, that's basically it. Let's say that. Let's just leave it at that. So the idea is each time step we receive a point, then we have to choose a prediction, a function, and then we predict, and we get to see the true thing. If we make a mistake, if it's not equal to the true label, if our prediction was different from the true label, otherwise we don't suffer a mistake, and then we proceed where each time the function is going to depend on whether we make it a mistake in the previous iterations or not. So good, that's like online learning, and the goal in this setting is, before we were trying to make sure the probability that we made the right prediction is large. Here in this type of setting, it's kind of similar. We want to minimize the probability that we make a mistake, or in this kind of setting, we make as few mistakes as possible. So we learn as we go. Good. So these are both, this is a related setting. We're more often going to be looking at this sort of general statistical learning setting. But this online learning perspective is another type of related learning problem, and it's something that'll be useful when we talk about Perceptron, which we're going to do now. So Perceptron, let's take a look back at this example that we just looked at. In particular, I want to go back to this classes example, something like this. Let's see, how do I copy this? So let's put this over here. And maybe let's take some of these scores here. Yeah, maybe we won't use them, but we'll see. Okay, so now let's talk about what might be a reasonable. I want to talk about first when the Perceptron algorithm is going to be useful. You still don't know what it is, but I'm going to give you a clear motivation as to why this might be a natural sort of thing that we'd like to do. So now let's suppose I keep giving you some data of this form. I keep telling you, what exam and homework scores people got and whether they passed or failed the class. Something's like, over here there's a plus, and over here there's a plus, and maybe even over here there's a plus, here, and maybe in terms of fails, we have something over here and here, here, and so on. Now, you might be noticing something, or maybe you can have some sort of prediction. Maybe in your head, you've come up with what the classification rule might be. So, in fact, you might be thinking that, okay, anything that's up and to the right is going to be a pass, and anything that's down and to the left is going to be a fail. In particular, maybe you'll draw, you could, in your head, have something like this. You draw a line here and say anything that's above is going to be a pass, and anything below is going to be a fail. Now, that's actually, and that would actually be a reasonable thing in the sense that you could imagine that the grading scheme for this class is going to be something like the following. If the average of homework and exams is greater than 0.5, so you sort of average over 50%, then pass, else fail. So that's maybe a reasonable way to consider a grading for a course. Now let's write this a little bit differently. Well, so if average of homework plus exams is greater than 0.5, so let's write that as follows: 0.5 times homework plus 0.5 times exam, and let's move this over to this side, minus 0.5 is greater than 0. Following, if this is true, then pass. And let's just modify it a little bit more. Let me write it even just a little bit differently. So let's say we want to do the following. So what we do is we write this as an inner product, the dot product of two things, 0.5, 0.5, comma, homework exam. And we want this to be, or sorry, minus 0.5. And finally, we'll write this as the following, sign. And what do I mean by sign? We mean that if this is greater than 0, we're going to have this be there. If this is going to be greater than 0, then this is going to be a +1. And if this is less than 0, then this is going to be a -1. There's, of course, some ambiguity about what happens at 0, but that's usually not a big deal. You can break those however you like. But that's interesting. So there's a very nice and convenient way to represent this function. In fact, let me just write it even simpler. Let's let xi equal the tuple of homework and exam. Now we can say the following. We can write this as follows, that yi is going to be equal to sine of 0.5, 0.5, comma, xi minus 0.5. Good. And that's exactly, and you might see that this is a very nice and convenient way to do it. The idea here is that you take your feature vector, you take the dot product or the inner product with some weight vector, maybe you have some offset, some additive bias, and then you take the sign of it, and that'll give you the label. So this is a very, very simple type of model that we can assume that our data follows. And if it follows this, then the perceptron will be a good model of this. So let me clarify a bit. Whenever we choose an algorithm or a machine learning model for a problem, we're implicitly making some sort of assumption on where the data came from. So when we're running the perceptron algorithm, implicitly it's going to make the assumption that the data comes in this form, something like let me say it like this. Implicitly, when we're doing perceptron, we imagine that the label is generated in the following form, that there exists some vector, which that we take the inner product with the feature vector, we maybe add some bias, and then we take the sign of the result, and that's how the label is generated. Furthermore, we make the assumption that the data, essentially, everything is kind of deterministically, the labels are deterministically generated like this, by a process like this. The sense that if there's something, we're never going to have, say, a blue thing on this side of the line, and we're not going to have a red thing on the other side of the line. Another way of saying this, we'll return to this in a bit, but we're implicitly assuming that there exists a linear separator which separates the positive and the negative examples. And that's kind of implicitly what we assume in the perceptron setting. Okay, so that's kind of the assumption that we're making on our data when we're going to be using perceptron, and when it will work well, when our data is linearly separable with pluses and minuses generated in this way. Okay, so here is the perceptron algorithm. Let's walk through it. It's a very simple algorithm, perhaps one of the most classic machine learning algorithms, like I mentioned. But we imagine that there's some data set, xi, yi pairs, which are, as we said. And there's going to be a few things. There's going to be an initialization that we have to specify, which it consists of a parameter or vector or a weight vector w, which is an r to the d, and a bias, which is just a real number, as well as some threshold delta, which is going to be greater than 0. So the idea is the following. What we're going to do is we're going to process our points one by one. So this is kind of written as if we're in the online setting, which we talked about before. But you can always imagine that if you're doing it in the classic non-online setting, where you're just given a batch of training points, then you just keep running this by, you simulate that yourself by picking points from your data set. But so the idea is at each time step, what you're going to do this process repeatedly. What you're going to do is you're going to receive a training example, whatever, from the data set. You can maybe pick it randomly. And what you're going to do is you're going to basically take the inner product of your point with the current weight vector, add on the bias term, then you're going to take the product with the sign of the label, or take the product with the label. And what you're going to see is this negative, or less than some threshold delta. In this case, it made a mistake, because recall, what we're trying to do is what we want to happen is we want the sign to essentially we want the sign of this product here to match the sign of the label. So if it doesn't match, then we'll have a negative product here, and that counts as a mistake. And if we make a mistake, what we're going to do is we're going to update the parameters. That is, the W parameter vector will be updated by basically adding on the feature vector multiplied by the sign of the point, and we're just going to increment the bias term by the sign of the point. Yeah, so now this might seem a little bit abstract, but let's see an example, and maybe this will make a little bit more sense about how this algorithm works. So let's start with a simple example where we just have the following. We have, say, 2 points, one which is 1, 1, and let's say x1 equals this, y1 equals let's say 1, and x2 equals -1, -1, y2 equals -1. Okay, so let's draw this. I think that'll be helpful. So what that looks like is something like the following, something like this. Have this and this. Okay, so let's run one round of the Perceptron algorithm where we first process this point, and then we're going to process this point if necessary. And what we're going to do is we're going to start with the initialization. How do we initialize our parameters? Well, a common thing to initialize, just start with, say, w is equal to the 0 vector, and that b is equal to the 0 point. Okay, and generally we take, I guess delta can be taken to be 0, just for simplicity. Okay, so what we're going to do is go through our training data, and we're going to start with this. And what we're going to do is we're going to take the inner product of, let's just compute this term here on the left. Well, we're taking the inner product of something with the 0 vector. So this will be 0, we're adding on 0, and we multiply by 1, but 1 times 0 is going to be 0. So we have that 0 is less than or equal to 0. So essentially what we did was we plugged in the first point into this expression here, and we saw that it made a mistake. It doesn't know how to correctly predict this. The first iteration is always kind of silly when it comes to Perceptron. But okay, so we basically saw that it's going to hit this if statement the first time. And what we're going to do is we're going to update the vector. So what we get is that w, this becomes w plus basically plus 1, 1, which is equal to 1, 1. And similarly, b becomes b plus 1, which is equal to just 1. So now what we have is some pair of w and b. And now we're just going to run on the second point. But before we proceed with going to the second point, let's see what this looks like. Let me try to draw for you what this classifier looks like. Actually, it's going to look something like this, in the sense that, yeah, it's going to look something like this roughly. So what this means is that if this essentially represents the line which has parameters 1, 1 and b equal to 1. And you can see that anything that's going to be on this side, anything that's up and to the right of it, is going to be plus classified, and anything that happens to be over here on this side of it is going to be minus classified. And I'm claiming this, you can check it for yourself, but let's just see by plugging in this point here. So if we plug in this point -1, -1, well, what happens? Well, this is just going to be, let's say, sorry, what will this be? We have 1, 1, so what we're going to do get is the inner product of W transpose W and X is going to be -2, and then +1. And then you multiply the whole thing by -1. And this we can see is equal to, this is equal to 1. 1. And we can see that this is not less than 0, so we don't have to update, and therefore we terminate. In the sense that we've gone through all our training data, and you can go through it all again and see it's all correctly classified. And indeed, you can see that in this simple example that they're both correctly classified. That's great. Now let's do something that's a little bit more exciting than that. Let me change one of these points a bit, just so that it's not as silly and we do more than one update. So let's change this to -1/4 and this to -1/4. Now, geometrically, what this looks like is this point is no longer over here. Now it's over here. So you can see now, even though we did this update, so okay, let's pretend we're processing this data point, this data set, and the first thing we'd do is we'd process this point and see that, okay, we similarly draw the line here. But now when we see the second point, before we didn't make a mistake, but now here, because we were going to classify everything that's above this line as a +1, well, now it's misclassified. So therefore, we have to make another update with this point. And more precisely, how do we know we made a mistake there? Well, all you do is just do the inner product of W and X. So that would give us, because we have 1, 1 and -1/4, -1/4, we have -1/2, and then plus B is 1. And then we multiply this by the yi, that's times -1. So this is equal to, this is going to be equal to -1/2, which is less than 0. So therefore, we made a mistake. And what we get now is we have to do another update. We do another update in the sense that we set W becomes W plus now the point. So, sorry, not just the point times its sign. So -1/4, -1/4, and then -1. And B becomes B plus the sign, -1. So what do each of these become? This becomes, say, 5/4. This becomes 5/4. And this becomes 1 - 1 equals 0. And so that's a new line. Now what would this look like in terms of being on this plot? Well, this would look something like the following. Okay, I didn't draw this very well. These should be parallel, but yeah. Something like this. And anything above it is going to be plus classified and everything below is minus classified. And you can see that now it went from something which made a mistake on this point to now, once again, we have something that correctly works. Like everything above is going to be plus and everything below is going to be minus. So this is kind of a toy example because we only had, for example, 2 different points. But this is kind of how the algorithm works. You can work out more complicated examples for yourself if you'd like. But that's the basic algorithm for now.